So this talk is about secure elements, but lately I've been using this trigger warning. This actually is not a joke. I use disturbing imagery in my slide deck just because that's me. I do that. So if you are squeamish about bugs or like creepy people, then you probably will want to leave. But if you're okay with that stuff, then stick around because it'll be fun, right? So anyway, who I am, a little brief overview for those that don't know. I think this is my sixth or seventh, something like that, time speaking at Hack in the Box. I love these guys. I've been coming to Hack in the Box for years and years and years. I first met them in 2004, 2005. Great team. But I am a longtime security researcher focusing on IoT, embedded systems, mobile technology, etc. First person to hack a car. I get to claim that. So that was me. I also wrote the GSMA's IoT security guidelines from a grant I got from the Department of Defense, which was pretty cool. Transitioned that material into what would become the baseline for the GSMA material, which we actually all worked on as a group. It didn't just come from my initial research. So, longtime researcher, longtime Black Hat speaker. I've talked at Black Hat 9 times. Like I said, this is my 6th or 7th year. So that's me. I now run a consulting practice where it's just pretty much myself doing independent contracting for IoT systems, security in general, and CPUs. But today, I'm talking about something a little bit disturbing, which I also find really cool. Which is basically identity in secure systems, right? Which is obviously a very fascinating topic and a topic that's growing more and more important over time. To me, this is exceptionally important just because my world is primarily CPUs and IoT. So in IoT, our number one issue is really determining what the identity of a particular device is, right? Like that's a baseline requirement for having an IoT network. And there's this really fascinating psychological issue called the Capgras syndrome. Is anybody here actually familiar with Capgras? Really? Nobody? Okay, so it's actually really fascinating. It's caused by several issues, mostly considered to be organic. But Capgras is essentially, you wake up one morning and you look at your wife, your husband, whatever, and in your mind, you truly 100% believe that that person is a fake. They look like your spouse, they talk like your spouse, they move like your spouse, but at your core of your being, you believe that that is not your spouse. That somebody has taken, a clone of your person and embodied them with, the psyche, the personality, etc., the underpinnings of a spy, essentially. So you believe that that person is a clone of someone you love, but that they're there as like a transplant, to like spy on your life. It's a fascinating psychological issue. It usually stems from schizophrenia or delusion caused by dementia as one grows older. But there have been a lot of problems that have been associated with Capgras that have come from really random areas, such as mild drug abuse, even, like if you've taken a psychedelic or ketamine. Apparently it's really predominant with ketamine. But how is that relevant today? It's really relevant because that's exactly what we're doing when we're attacking identity in IoT systems, because you basically see this little device sitting in a corner of your house, right, or your office or whatever, your car, and you believe that the device is exactly the device that you think that it is, right? Except over time, you feel like, that really doesn't seem like it's my device anymore, but I can't tell you why. Does anybody ever get that feeling? A lot of security researchers get that feeling. And it's usually because we're around devices for so long that we recognize patterns. In fact, my first corporate job was a security engineer for a large embedded systems firm. And I could tell you when our build server was going to go down by the second, because I knew if it went over, if a build took longer than 5 minutes and 29 seconds, it's because something caused the build server to crash. And so I could literally call it. when a build server was going down. And people in our industry just kind of get used to those patterns over time, right? And you sense when a device isn't actually doing what it's supposed to be doing. And that's kind of like an analog for Capgras syndrome in our environment. We know that the device isn't behaving the way that it should be, but why? Why isn't it behaving the way it should be? Well, this is really a demonstration of that. So what's really fascinating to this about me is, fascinating to me, is the implementation of secure elements at scale, right? Because that's really the important thing. Like, anybody can secure one tiny device, at least from a secure element perspective. It's not that hard. It mostly comes down to configuration. But when you're doing it at scale, it's extremely different. So if you're a large manufacturer like Samsung or Apple or Microsoft and you're using secure elements at scale, it's extremely difficult to do it correctly. And so the Capgras syndrome here is really a perfect analog to me of how you can create those strange flaws, those strange gaps in what occurs in scaled environments. So this is an attack against Apple's WAC. Is anybody familiar with WAC? No? Great, because it's fairly new. In fact, WAC is so new that it still requires an NDA to learn anything about it. I reverse engineered a lot of WAC through my practice consulting with other organizations. I don't get access to any of the MFI libraries. I don't get access to any of the WAC libraries. I just get devices. And then the devices, I basically have to reverse engineer and identify how they're provisioned, how they're secured, how they communicate with the network. So I am not under NDA with Apple. I have never read any of the specifications from Apple. And this talk is basically a demonstration of how Apple has flaws that allow you to burrow pretty much into any network that Apple enables secure provisioning for. So what's really fascinating about this is WAC is designed to allow accessories or IoT devices access into your world. And by your world, I mean an iOS device should allow, over WAC, some IoT accessory to connect to your Wi-Fi or to connect to other devices securely using a Bluetooth security key, right? So that's essentially how it works. It's a baseline provisioning system so that you don't have to sit there and type in a Wi-Fi password to a small device that really doesn't have a great user interface. IoT has a serious problem with that, and this is kind of the solution for it, is that kind of deployment. So attacking WAC is super easy, and I didn't really think it was going to be this easy. It's both easy and it's hard. I should qualify that by saying it's easy for me, but it will be easy for you too, and you'll see why, because I've developed some tools that make it super, super easy for everybody else. So this is essentially WAC. Who has seen this before? Anyone? One person. All right, well, you're going to be seeing it more. So when you have an IoT device that you need to connect to your Wi-Fi network, you turn it on, and the first thing it does is send out a beacon saying, "Hi, I'm a Wi-Fi access point." But there's a special code according to the Apple's WAC specification that tells the world, "Hey, I'm an accessory device and I can be configured with iOS." So who has an Apple device on them right now? Probably a lot of you, yeah? All right, we're going to test something just because I'm curious. Because I've never done this in the EU, I don't know if there are configuration parameters that won't allow for it. I have no idea. But everybody go into your iOS, go to settings, go to Wi-Fi, and if you scroll down past the networks, you should see set up new device, and it should say LOL Don. Does anybody see it? All right, most of you see it. So this is basically tricking iOS into thinking that you are a WAC-enabled device, okay? So my laptop right now is supposedly a WAC-enabled device. But if you're a WAC-enabled device, you're required by Apple to have a thing called an MFI chip. Who's familiar with MFI? Anybody? Great. One individual. So MFI is essentially Apple's secure element for provisioning. I think they use it for multiple things. They use it for certificate chaining, other stuff. I don't really know because, again, I don't have any documents. I'm not under NDA. But point being, in order for provisioning to work, you have to have one of these chips. So this secure element basically allows your iOS device to communicate with that particular accessory. So say I had an internet-enabled toaster, okay? That internet-enabled toaster would have that little Apple MFI secure element chip on the circuit board. And when it presents that Wi-Fi interface to your iOS device like this, your Apple device will say, okay, I'm going to connect to that particular device and talk to that chip directly. So over HTTP, it will actually send messages to a little embedded application on your toaster that will then communicate with that MFI chip. And that will allow the MFI chip to securely sign a message saying, yes, I am a real Apple MFI chip, and here's information that allows you to trust me. At that point, iOS will say, oh, cool, I can trust you now because you are an authenticated Apple MFI device. And it will provision all of those security keys for joining the Wi-Fi, joining whatever network over that secure tunnel to the MFI chip. Okay? Now, the application, the toaster itself, the toaster application, so to speak, is not supposed to be able to see any of this data. The MFI chip itself is supposed to contain all that information. So it should be storing those secret Wi-Fi keys within the secure element itself. Okay? But who can guess what the gap is in this process? Anybody? You can shout it out if you actually figured it out already, because it's pretty obvious. At some point, the toaster needs to know what the Wi-Fi password is in order to connect to the Wi-Fi network that it's been provisioned to, right? So MFI can't just keep all these secrets secret. They have to let the toaster know what's going on. The problem is the toaster's in the non-secure world, right? It's just got a simple ARM Cortex-M0 Plus on it. There's no secure storage on that device. So essentially what you have is an IoT device that receives information that's sent to an MFI chip that holds it in escrow essentially, but then it's given to the toaster, whatever application it is, as needed, right? So when that toaster needs to connect, it just says, hey, MFI, give me the info, and hands it off to the Wi-Fi adapter, and the Wi-Fi adapter does the rest. But that key has to be shared, right? And that's the important part of the hack. So what we end up doing here is we just have a very, very simple test harness, which is essentially your laptop with host APD on it, so you can simulate a Wi-Fi access point, or become one, not really simulate one, right? But you're simulating the WAC accessory model. And what you actually do is you become man in the middle between iOS and an actual accessory. Now, you might think to yourself, hey, Don, but isn't that exactly what encryption is supposed to stop? Man-in-the-middle attacks? You're being ridiculous. Yes, except that it's very important that we have man-in-the-middle access for one particular reason. If we use a man-in-the-middle attack here on a hacked accessory, we can essentially ask the accessory to give us all the provisioning we need in order for our laptop to join the network. Because again, the MFI chip has no idea what the difference is between the ARM Cortex-M0 on that accessory and another processor or device that's connected to the accessory. It can't differentiate between the two because secure elements that are small external secure elements communicate over a physical bus protocol. It has no idea whether that physical bus is local or whether there's a device attached to the physical bus that's been ported over a network connection. In other words, to your laptop. That chip has no idea. So you can basically trick it into provisioning access to whatever you want and acting as a proxy for you in any network that you can get access to, which is pretty cool. So step one, all we have to do is use host APD. And this is really easy. Even if you've never used host APD before, it's the simplest command ever. All you have to do is type host APD. That's it. So there's a configuration file that comes along with it, but by default, you can literally use the default configuration. There's nothing special that you have to do in order to run host APD. But in order to spoof a WAC instance, you do have to adhere to Apple's specification. So vendor elements, anybody here familiar with Wi-Fi vendor elements at all? No? Okay, so this is how vendor elements work. If you're familiar with Wi-Fi packets in general, they have a TLV format, type length value. So essentially, when you see Wi-Fi beacons on the network, it's just a series of bytes. And those series of bytes indicate certain types, as in, hey, this type tells you what the SSID is, or this type defines what speeds this particular access point allows, or this type indicates something else. But one type, 0xDD, indicates vendor-specific elements, and that's where WAC comes into play. WAC is defined by a vendor-specific element according to the Wi-Fi specification. So the Wi-Fi specification says, if you have a vendor-specific element, just mark it as type 0xDD. The next byte is the length of the payload. And then the 3 bytes after that indicate the OUI, or vendor, that has specified this particular data type, as in this is this particular manufacturer's special data format. So for WAC, it's really easy because literally all you have to do is just add a payload that adds the Apple OUI, 00A040. That's it. Now, any iOS device is going to see that and interpret that as a WAC configuration. And I really can't find anything else that forces this configuration to be processed in this fashion. In fact, most of these element data packets are not actually required, which is weird. So anyway, you can define the SSID, you can define the MAC address, you can define description, the vendor name of whatever this device is that you're spoofing. But it doesn't really matter because, again, this is all completely in the clear. None of this is authenticated data. So you can say whatever the hell you want. And more importantly, the SSID of whatever you're presenting can be anything you want too. So if your toaster is like a Bosch toaster, right? You can literally just put Bosch toaster in your SSID. But in your WAC information, you can call it ha ha ha. It doesn't matter, because apparently iOS doesn't give a shit. So it doesn't really check any of these things. All it checks to determine is whether or not it is a wireless access configuration enabled device. And if it is, it presents it in that list you saw in settings. Okay, so to make this easier, I just wrote a simple little Python script that I'll put up on GitHub after the talk. But, you know, it's in the slides. You can just copy it. It's only a couple of lines. But this is basically a little file that generates the configuration for you. So all you have to do is just put your name that you want at the top, and then run this script, and it'll auto-generate the payload that you have to put into host APD. So super simple, right? Like you can just do this in seconds. And then here is the actual payload inside the host APD configuration. And this is it. This is just the encoding. It's literally just hex encoding. That's all it is. It's nothing special. But the script just generates the actual payload data on your behalf so you don't have to do it by hand. But essentially, when you use that, like I just did with my laptop, your laptop will become a wireless access or accessory configuration device. And when iOS connects to it, it starts sending MDNS requests. Those MDNS requests that are circled include MFI configuration. So it's basically searching the network saying, okay, you're saying you're a WAC-enabled device, but in order for you to be a WAC-enabled device, you have to have an MFI. So it's searching for the MFI service. And all we have to do at this point is respond with the information saying, yeah, I'm an MFI service. Now, at this point, you have to have encryption, which means that you have to have the keys that are stored on the MFI chip itself, which you don't have, right? Unless you actually get access to the physical strata of the MFI chip, which we're not going to do. Because that would require us to do actual work, and that sucks. So instead, what we're going to do is we're just going to play man in the middle. And this is super fun. So I wrote a great Python script that I use called MOOPS, or My Object-Oriented Packet Spoofer. It's up on GitHub, and it's super easy to use. And basically, all you have to do is relay frames, right? Because MDNS uses multicasting. It's multicast DNS. And MDNS, or multicast in general, is a pain in the ass to forward over networks. Does anybody forward multicast data over networks? It's a huge pain in the ass. You really can't do it by default in the Linux kernel or any other real kernel because multicast is supposed to, by definition, stay on the same network segment that you're on. You can forward it a little bit, but you're not really supposed to forward it bidirectionally. Point being, we need to be able to forward it across networks because, again, we've got two Wi-Fi networks. We've got one that's presenting as a client, and we've got one that's presenting as a host, AP. So we basically have to tell our accessory device that we're spoofing, hey, I'm forwarding data to you, and I need the response so I can forward it back to iOS. Okay, so that's my little application Fling does just that. So basically, it's just a Python script that uses MOOPS, and it sits on top of your Linux wireless interface and just presents a raw packet interface to the interface that your host APD is running on. So as soon as messages come in, multicast messages come into the network from iOS, it just rewrites the packet and sends it on the appropriate interface that's attached to your target device. Super easy, right? And this is the script. Now, using my MOOPS packet library, this was super easy because MOOPS is basically like a TCP IP stack, but if you were to write it in Python, so it's all raw, it's super simple. But this is basically the script that you have to use to forward packets back and forth over multicast across bridged Wi-Fi networks. So as you can see, it's really small. It doesn't take much. But this is literally all we need in order to forward those messages back and forth. But what's great about this is that now iOS has no idea that it's being instrumented, right? So it's forwarding the data back and forth, everything's good, and we're just sitting in the middle with our laptop. So now we can do all kinds of auditing here. This is where you would drop in a fuzzing architecture, some kind of harness for doing other types of testing if you wanted to try fuzzing the MDNS stack. There's an HTTP stack. It's not HTTPS, which of course it can't be. Where would the keys go, right? So essentially, when you have this set up this fashion, it's pretty much done. All you have to do at that point is hack an actual endpoint. So pretty much any IoT device that has an MFI implies that it can be hacked. Anybody want to venture a guess as to why? Shout it out if you know it. It's using MFI. It has to use a third-party vendor's chip, Apple's chip, because it's basically saying, hey, I can't secure my own shit. I need someone to secure things for me, which basically means that you can hack the hell out of it, right? So most of these devices just have a simple ARM chip. In most cases, ARM Cortex-M that's just running an embedded systems platform. But it's not really enough to do a lot with. So usually what I do is just flash a little application that relays data over, say, a serial port, like a UART or something like that, right? There usually isn't a lot of room on the flash of these devices. There isn't a lot of security either, so you can usually just flash your own application that after boot up, it runs and it starts instrumenting communication between your laptop and the network. So basically, like, you can use it as a network device, or you can use it as a serial device, or you can do whatever you want. But the best case scenario is you've already got man in the middle, so you're already basically talking to the application on the instrumented accessory, right? So if you just add a little application that says, oh, when you hit this web page, it's going to respond with, say, keys for provisioning to the actual network that you want to hack, right? And that's what's really great here, is that once you have that little application there, you can basically tell the MFI to do whatever you want. And now you have the ability to set up a harness where you can do fuzzing, you can attack iOS, you can attack the actual MFI chip, you can attack the infrastructure around it, you can tell the MFI to provision you keys to join whatever Wi-Fi network is relevant. All of that stuff is pretty much 100% in play now because you have the infrastructure set up in order to do that. The long-term game is really to just have the device do it on your behalf so that you don't actually have to do the man-in-the-middle thing at all, and you can kind of just connect to it and say, give me the keys, if it's already provisioned. A real-life attack scenario for this would be basically sitting outside of somebody's house that already has devices that are enabled with this technology, and you would essentially say, oh, okay, well, I'm going to DOS whatever that thing is that I'm targeting. It's going to disconnect from the network. The person, when they go to use it, isn't going to actually see it on the network. So they're going to check their phone and they're going to re-provision it, except the next time they're provisioning it, they're actually provisioning my device, and they're giving me the keys. Now, that's not a great APT flow. So if you're an actual offense person and not a defense person, it's not the best scenario for attacking somebody. But it's a relevant scenario architecturally because it's still a significant security flaw. The result of this is that basically you can impersonate any whack device anywhere because there is no ability for iOS to understand, what device it's actually connecting to, right? And I'll describe that a little bit more in depth. So this is really a fascinating thing. How many people here work with secure elements or IoT systems in general? Probably only a few people. Yeah, it's not hugely popular in our circle. But what's really cool is it's basically like the blind leading the blind, right? Because you have a system that has absolutely no idea where it's getting data from. All it knows is that it's really, really close to the device, as in close as in intimate with it. It's supposed to trust it, right? So there's a presumption of trust. There's a presumption of safety. But really, each device is basically just hiding details from the other device that the device really, really needs in order to function. And they just kind of trust each other to do the right thing. But it's all based on flawed architectural models. And these are the flawed models, okay? So there are essentially 3 models in secure element design. And since most of you don't work in IoT, I'll explain them here. So these are simple threat models that define these architectures, okay? So in the most basic model, there is no secure element at all. This is pseudo-secure element. This is basically you have a device whose cryptographic keys are stored in flash somehow, okay? They could be encrypted in flash. They could be plain text in flash. It really doesn't matter. Even if encrypted keys are encrypted with another key and stored in flash, who cares? It doesn't really matter because there's no secure way of hiding that information from anyone. So all a reverse engineer has to do is take a few extra steps to find the extra key to decode whatever the encryption keys are that are stored in flash. It's useless and it's busy work, and it takes a lot of excess time to develop this kind of pseudo-security to make it somewhat presentable to production. There's no reason to have this in production ever, except that's pretty much primarily what you'll see in production because it's more cost effective. It doesn't require a secure element, right? So you should never see this in practice, but this is what you will always see in practice, essentially. But the model is very simple, right? You've got an insecure storage medium. This is flash or EEPROM or something else that's storing the actual keys. It's attached to what's presumably a privileged set of processes in kernel. And the kernel applications themselves create a ring of protection around the insecure device. That's the idea, right? So applications themselves can't necessarily be attacked. So a privileged and unprivileged application inside the operating system on the IoT device will not have direct access to those keys in Flash. But as we all know, that's not the reality. The reality is that in order for this IoT device to function, it needs access to those keys. It needs to be able to perform services based on those cryptographic keys. So in the real world, the privileged userland process will usually directly require the keys from kernel and just say, hey, kernel, give me access to whatever the secure element is, in this case, EEPROM or whatever. Privileged userland process gets the keys, hands them off to the Wi-Fi, whatever, connects to whatever needs to be connected to. In rare cases, you'll see a kernel module that actually does this on behalf of a privileged application. That's really rare, though, because it requires excess work that most people aren't really willing to do. So mostly what you end up seeing is a privileged device in the kernel, and the only type of security here is really just you have to have administrative access on the operating system to read this device. That's it. So this is important for two reasons. Number one, it implies that any physical access to the device will acquire access to the keys, because there is no secure storage for the keys. There's no secure memory at all, right? And because of that, we can extract those keys from Flash without ever having to boot up the operating system or attack it in any way. There's nothing to do. We can just read it straight off Flash or EEPROM. Easiest thing you'll ever do as far as offense goes. Now, if you can't do that for some reason, as if you're attacking it remotely, then it's super easy if you can land read capability from the device, or if you can get code execution on the application and really act as any application at all. Because in a lot of these architectures, even the unprivileged applications are the ones that actually interact with the real world. So what ends up happening is an unprivileged application can ask a privileged application in userland, hey, I'm going to go talk to some peer or a backend system to do updates or whatever. I need access to the cryptographic key to perform some kind of signing operation. It'll ask the privileged application for help, which will then retrieve the key from Flash, which will then help perform the operation on the unprivileged application's behalf. So in these models, you technically don't even have to have access to the privileged application or the kernel in order to do anything useful. Because to be useful, the applications have to have access to the keys somehow. So they can just ask for permission. Hey, I need to do this. Give me access to it. Okay, fine. Here's your key. Done. So the attack model for this is really straightforward. Physical access is 100%. Application access is 100%. And if you're reading off memory, if you have some kind of a vulnerability where remotely you can read memory off the device, then it's usually game over at that point too, because you can just read the places in memory where the key's been stored. Done. Now, in the non-operating system model, things are a little bit more interesting. And they're more interesting because obviously they're simpler. But it's also interesting to me because as an IoT engineer or system architect, this model is actually a little bit more fun because it requires more work on the behalf of the attacker. Because you don't always have a real-time operating system running in userland in the kernel. Sometimes it's just a standard application that the engineers have handwritten. And then you actually have to do something interesting, like reverse engineer a real application that does something that you've never seen before, which is cool. It's fun to actually do some kind of reverse engineering that takes a little bit of thought. But most of these are architected in the same way anyway, because it's all basic, ARM imagery. So, you see one ARM image, you've seen them all. But the applications themselves are always a little bit unique based on what the engineer thinks is important. So you have to do a little bit of reverse engineering, but you can still perform the exact same attacks here. The architecture itself is no different in the non-operating system version than the operating system version. In the external element model, which is what you have in MFI, this is really cool because now you have something that you can't physically attack in some cases. So in a secure element model where you actually have a chip on the board, or the external element model, in this case, you're presuming that the chip itself does not allow physical access to the keys. So it's not like reading off of flash or reading off EEPROM where the data is just going to be in the clear. You're not supposed to be able to get keys off of a secure element ever. It's supposed to be on there, period. The only device that actually knows how to interact with it is the secure element itself. So all you can do is make requests to the secure element for information, for signing, for verification, etc. And it will act on your behalf. But aside from that, you actually can't do anything else with the device. So in this case, physical access in some cases is relevant because certain secure elements, you can attack it over the bus because there isn't actually a way for it to guarantee that you are who you say you are. As in, say you have a secure element on a board and the secure element is only authorized to communicate with, an application that's running on firmware. Well, the application that's running on firmware needs to store that key to verify itself, right? And again, this application in firmware can't store its secrets anywhere that you can't get because, again, it's an insecure chip. That's why there's a secure element there. So you can read out of flash from that particular device, get that key, and then communicate with that secure element. Easy breezy, right? So in some cases, in this model, you actually can attack that physical device over the bus. But again, it's not a physical attack as in you're just going to read something. You've got to actually have it turned on. You have to interact with the device. You have to adhere to the application specification or the API. There's relevant steps that need to be taken in order to interact with it. And it doesn't always work, depending on how it's been architected. But regardless, this is actually a fairly more secure model because you actually have to land code execution in user land or kernel land and then bridge down into the secure element from there. You have to tell the architecture, hey, perform requests on my behalf. If you have a properly provisioned IoT environment, then the IoT device itself will have a unique key that's stored in flash. So if you pop flash on one device, you don't know all the secure element communication keys for all devices in that fleet. So then you won't necessarily know exactly how to communicate with all of them, and you have to pop each one individually. That's a huge pain in the ass, but you really never see that in practice because it's very, very hard to do that at scale. So in this model, it's more secure, obviously, than the flash model, but it's not secure because, again, the external element has absolutely no idea what applications are running in kernel land unless there's a security key. And if there's a security key, it can be retrieved by you because there's no security store on this device. And if there's no security store, or you have to verify the application running in kernel land and user land, that can be instrumented. And has anybody seen the recent Ledger Nano S hack? I'm going to forget the kid's name. But essentially, one of the best attacks against this model that I've seen in recent times was performed against the Nano Ledger S. So Salim Rashid at SPUDOWIAR, I don't actually know how to pronounce his Twitter handle, which is why I had to look it up. But Salim basically performed an attack against this model against the Ledger Nano S. Now that's really important because Ledger Nano S, as some of you might know, is a cryptocurrency hardware wallet. But basically he proved, because they use this model, that you can man in the middle any Ledger Nano S that you get from Ledger. So even if somebody sends it from Ledger, if you are the NSA or you're another, three-letter organization, you can intercept that shipment, perform the same attack that Salim did, implant your own firmware, and then ship it on forward to the recipient, and the recipient has no idea because they think that it's still secure. When they boot it up, it'll actually act like the normal device because the secure element believes that the ecosystem, the environment that it's running in, is secure. But again, the secure element has no idea. It has no direct access to memory for the actual application processor. There's no way for it to make any guarantees about the application environment that it runs in. So it seems more secure, and it is more secure from a physical perspective. And by physical, I mean you cannot get all the keys off of the secure element itself. However, the disconnect between the application processor and the secure element are enough that you can always create an attack between these two architectures. So in the Ledger Nano S model, what they did was they basically said, all right, we're going to verify our chips by forcing the application to send an image of the entire range of flash memory to the secure element. And the secure element will then verify us by saying, okay, the entire range of memory has been provably verified and signed. So it basically says, all right, this is the executable image that I expect to be running on the kernel, on the application processor. Therefore, I will unlock myself and give you access to keys. But again, the problem is that if you actually have your own application running, your own implant running in Flash on the application processor, you can tell the secure element anything you want. So what Salim did is basically found ranges in memory where the data was the same. And he overwrote those addresses with his own implant. And then when he was booting up, he basically just sent images of the application processor's flash to the secure element. And whenever he hit his own regions where he had his implant, he referenced the areas of memory where the copy already was. So he was able to basically just trick the secure element into unlocking itself and hiding his own implant by abusing those copied regions of memory, which was actually a pretty brilliant attack. And it was necessary because there's only a small amount of flash available in that environment. So he had a little amount of memory to work with. But again, in this model, there is absolutely no way to provably secure the application processor from the secure element or the secure element from the secure processor or from the application processor. There's no way to do it. So in this model, it will always 100% be broken, which is exactly the problem you see in MFI. And the reason why I was able to break MFI so easily, and I'll get back to that in a second. The third model is the internal element model, and this is the trust zone model, okay? Now, this model you would think would be more secure because the processor itself has the secure element on the inside of the processor. So the first thing that occurs is that you get booted into a secure world where the secure processor or the secure side of the processor knows, oh, the code that I'm executing right now has been verified as guaranteed to be trusted because it's usually a read-only memory image that's inside of the processor's core. As in, like, this isn't the application layer at all. This has nothing to do with the customer or the application. This is something inside the processor that will make guarantees about the next stage of execution. So usually what happens is somebody puts their own keys inside of the secure element, trust zone, whatever you want to call it, and then the first stage loader in ROM will actually do the initial trusted verification of that next stage image. So the application image, the next stage bootloader, or the trusted bootloader, will be signed and verified, and the ROM image will actually perform the verification. Now this is all good, and this is proper process. Like, this is what we should be doing, except that trust zone is extremely expensive, which is why that you don't actually see it deployed everywhere. It's not open. It's a pseudo-open specification that most implementations of require an NDA. And even if you have the NDA, you still don't get full access to all the documentation on the trust zone implementation. You only get access to the pieces that you need to build a secure application or to interact with the manufacturer's secure implementation. And that's really important because in this model, it's flawed as well for those reasons. Trust zone, or the secure world inside trust zone, is a black box. You cannot see it. Essentially, the way it functions is the virtualization of the ARM processor creates two separate worlds. It basically creates two virtual CPUs. One's normal world that runs your Linux operating system, and one's secure world, which usually runs some kind of simple application or a real-time operating system that runs some kind of secure API. And what ends up happening is the secure world lives in a black box that the normal world cannot see. And the normal world just makes traps or interrupt requests to secure world for information saying, hey, I need to sign something or I need to verify something. Can you help me? But the normal world has no way of really verifying that secure world is secure. And it has no way of verifying the identity of secure world. And that's more important, because it's kind of the opposite of the previous model. In the previous external element model, the application processor is always insecure. And the secure element really has absolutely no way of verifying the identity of the application processor, because the application processor can always trick it. But in Trust Zone, the application side can never truly verify the secure side. So in this model, as an attacker, all you have to do is just have a malicious secure world. So if you want to deploy an attack against an application, you basically just say, I'm a secure world, I have trusted keys, and you can trust me. But the application side doesn't know. All it's presuming is that it lives in a CPU environment that has been made guaranteed by Trust Zone and by the manufacturer. So it just basically says, okay, you've got certificates, great. Those certificates are clearly a part of my infrastructure, and any external device that uses those keys, I'm going to trust it. Right? So it's still a flawed model. And if you can attack the secure world in any way, you can still basically instrument the communication between application world, secure world, and any external entity. So that's a really important thing to understand, that Trust Zone is inherently damaged from a security perspective because it's not open, it's implementation dependent, variations on implementation will result in wildly different variations of secure. In fact, a really great attack, a common attack against Trust Zone implementations, is that Trust Zone implementations don't always secure DDR RAM. A lot of them don't bother because it requires extra expense to be able to secure the DDR RAM bus. So only some implementations will actually have a secure world version of DDR RAM segmented by physical memory, and then there will be a normal world of RAM. The first thing that you can do booting up an application world if you have full access to DDR RAM is start reading the regions that you're not supposed to touch. Done. Usually you can start extracting keys from those environments. So because of that, because of the NDAs required, because of the black box nature of secure world inside Trust Zone, it's not only expensive and cost prohibitive to actually deploy, but it really doesn't give you the secure world you think you're getting. It's extremely damaging, in my opinion, to security because there's no openness to it. It results in inaccurate and incorrect secure architectures that aren't secure at all. So essentially what we're doing now is eating our bugs, right? You understand the architectures themselves, you understand why they can be attacked, so why is this useful? Secure boot, attestation, self-identification, and peer identification. Those are the basic models that we have. And because of the issues that I just described, you can't do secure boot in a flash-only operating system, period. There's no way to do it, right? Because the whole point about secure boot is that you're going to trust all the executable code that you're going to execute. If you don't have a secure element, you can't do that, period. There's no way to do it. Anybody can alter flash and then just tell your secure boot that it's okay. In the secure external element model, again, there's no way to do it because the secure element can never trust the data that's in the application processor. No way to do it. In the Trust Zone model, you can get secure boot, but you can only get secure boot for a couple of stages. As soon as you get unsecured applications running, they can make no guarantees as to the identity of the trusted elements that have executed before them because of the black box model of Trust Zone. So in essence, The 3 models that we currently have for secure elements are failures. 100%. Attestation is the same way and for the same reasons. You can't trust them, right? The whole idea behind attestation is you're sending requests remotely to an endpoint to verify that its environment is stable. And there is no way to make those guarantees because, again, these models are all flawed. Since none of these architectures can be trusted and none of the applications can trust the secure architecture and vice versa, there's no way to perform attestation in a way that's actually fully reliable. Identification is the exact same way. How are you going to perform identification if you can't actually trust any element of your architecture? Right? And the identity is really, really important because that is the core of MFI. The core of MFI is saying, oh, I am implementing a concept of identity on behalf of iOS and on behalf of applications or accessory devices. But because as we just saw in the secure element model, the external secure element model, the secure element model in external secure element model can never trust the application processor. Therefore, the identity that's proven is only the identity of the secure element and never the identity of the application. Thus, you will always have a break between, well, we can't execute that now, can we? Oh well. Well, you always have a break between the actual application processor itself and the secure element. Those two identities are then completely separate. And because the application processor cannot then be securely identified, there is no way to make guarantees as to what device you're actually talking to. Only that the device that you're talking to is enabled with WAC and has an MFI chip. That's it. So in essence, the Apple model is flawed because it does not present a clear chain of identity between the network, the application running on the accessory, and the secure element that's attached to it. The only thing that can be secured is the MFI, and the only data that's on the MFI is for Apple, not the application. So essentially, if you've hacked something with an MFI chip in it, you can port that to pretty much any architecture that you want. Can somebody tap the screen so they can get this animation working? This would work a lot better on my iPad. But AV fails. What are you going to do? Point being, well, that's not what I wanted. That's fine. Whatever. Point being, Apple's MFI is problematic from an architectural perspective because they can never make guarantees about the identification of the application that you're or the accessory that you're connecting to your network. So when you see a device that you've brought home from the store and you connect to it and you provision keys to it over this method, you don't actually know whether it's the device that you're provisioning. It could be something that's actually performing a man-in-the-middle attack that's then abusing a flaw on that architecture to steal the keys from it and then using that to connect to your network as well, which is really fascinating, right? The other thing that's important to note about MFI and these models in general is that they don't just apply to Wi-Fi. So I perform the attack over WAC or Wi-Fi WAC, but in essence, you can perform this attack over any medium where the network is disconnected from MFI. And that's going to become more and more important over time because they're going to be using MFI for provisioning over Bluetooth, over Lightning, over other medium. So essentially, you could perform this exact same attack over any other network protocol because there's no tie-in to the network protocol and the actual application and MFI chip. So this is really a Wi-Fi only attack. It's an attack against secure elements in the Apple architecture, which is presumably portable to all these different other mediums. But I have not tried that. Your mileage may vary, but I do request that you go and check it out for yourself and let everybody know the result. My point in doing this research was essentially to prove the secure element models were flawed and flawed in a specific way based on the GSMA IoT research that I did with the GSMA back in 2015, 2016. We published the document called the GSMA IoT Security Guidelines, which I wrote in concert with most of the GSMA. And the threat models for secure elements that you saw here were actually developed during that time. It was based on some of my DARPA research from before, but essentially it was based on the GSMA research. So this was really an exercise in proving how deploying secure elements at scale creates this disparate environment, or environment of disparate technologies that cannot truly identify or communicate with each other, right? And that's really a function of scale, because it's, as I said at the beginning of this talk, you can secure a device in any fashion as long as you only have a small amount of them. But once you get to the scale of Apple, you can't individually provision every single device. That causes a very large and substantial change to your manufacturing process as a whole. And because of that, that increases your costs. It increases the lifetime of production. It increases the potential for flaws and failures in your architecture. It also creates the possibility of bricking your devices themselves, because now every single device has a unique key that's dependent on the secure element being working properly. A lot of things can fail unexpectedly. So getting that architecture up and running is very difficult. The manufacturing architecture is extremely difficult. So it's understandable that they would have this flaw, but it was important to prove it so that we get to better and better models. I've been working with Apple on this issue, and I dropped this information to them about a year ago. So they've had almost a year to work on it before I began talking about this. I wanted to give them ample time, because even though it's not a super critical issue, it is and it's not, right? Like you can attack people remotely. You can attack people in their homes. You can use it as a way to get backdoor access into anybody's home network that uses Apple technology. But you have to be there, you have to be physically present, you have to know which device you're attacking. There are a lot of ifs. So even though it is kind of a backdoor, it requires a lot of steps and physical access to at least proximate physical access to the environment. So I gave them as long as I could to talk before I talked about it. But a situation like this requires so many different teams to resolve, because now you've got the MFI chip team, and you've got the MFI protocol team, and you've got the application specification for WAC team, and all these other organizations that all need to work together and define an engineering process that completely resolves all of these issues, as well as defining a new manufacturing specification that allows for all of these security keys to be unique and tied to each specific accessory. It's nuts. Right? That's a very, very difficult and challenging thing to do. So it's understandable that it took them a very long time to implement it, and it's still not fully implemented. So this bug will be around for quite some time. So if you are an iOS hacker and you're looking for a jailbreak, MFI is definitely one place to start looking. But in essence, that's about it. Apple's got some serious problems, but they're no different than any other architecture that's deploying secure elements at this scale. They are no different than Samsung. They are no different than Microsoft. They are no different than anybody else. So this isn't really a bash Apple thing. This is more just a, Apple tried to deploy a secure element that was really easy for me to hack kind of thing. But yeah, that's it. So I appreciate your time today, and thank you for checking out the MFI talk. And we've only got a minute or so, but does anybody have a question about anything that I've discussed today? If you do, feel free to come check me out at any point in the conference. I'm more than happy to talk to you separately. Thank you.